Patty Simpson with Simpson Math. In this video, we're going to graph a polynomial. We're going to start by looking at the end behavior and kind of get an idea of what this polynomial looks like. So when we look at the end behavior of our polynomial, we begin by looking at the leading coefficient. And the leading coefficient is just the constant on the term with the highest exponent. So we look along, and this one has the highest exponent. So our leading coefficient here is a -12. That -12, what we care about that, what's important about the -12 is the fact that it is negative. When our leading coefficient is negative, we know that on the right it's going to fall. If it had been positive, then on the right it would rise. But because it's negative, it's going to fall on the right-hand side. So our leading coefficient lets us know what's happening on the right-hand side. Then, next, we want to know what's happening on the left-hand side. To find that out, we're going to look at the degree of our polynomial. The degree of my polynomial is just that highest exponent. This is a third-degree polynomial, or a cubic. What I care about that 3, or what's important about that 3, is the fact that it is odd. When my degree is odd, then we have opposite end behavior. If the degree is even, then we would have same end behavior. So in this case, I have the opposite end behavior. If it were an even number, we would have the same end behavior. But I have opposite end behavior, so I know on the left, since here it falls, we do the opposite, so we are going to rise on the left. Then there's a few other things that we can just look at the equation and find out about this polynomial. This tells us what's happening on our ends, but we can tell a little bit about what's happening in the middle of our polynomial also just by looking at the function. Because the degree of the polynomial is 3, we know that 3 minus 1 tells us the number of terms that we expect to have. 3 minus 1, there should be 2 terms in this particular function. Then, because there are 3 roots here, 3 is our degree, then we know that there are going to be 3 roots. And later when we find our x-intercepts and we write it in linear factors, we should have 3 linear factors. So that's step 1, is we find the end behavior. And we can even give a little sketch. So I just call this the end behavior. And it gives us an idea of what our graph's going to look like. We know it's going to fall on the right, it's going to rise on the left, and there are going to be 2 turns, 1, 2 turns. So our function is going to look something like that once we've graphed it. Next, we're going to look at the y-intercepts. So remember, with the y-intercepts, that's where the graph intersects the y-axis. And along where that y-axis, the y-axis. And everywhere that y-axis is, our x values are equal to 0. So anytime we're looking for the y-intercept of any function, we can just substitute in 0 for our x to find that y-intercept. So I'm going to take my 0 and substitute it into my function. So evaluate the function where x is 0, and I have -12 times 0 cubed plus 4 times 0 squared plus 3 times 0 minus 1. So everywhere I saw an x, I just substituted in a 0. This is 0, that's 0, this is 0, so it just leaves me with a -1. There is a point on my y-axis at 0, -1. I'm going to write that y-intercept as a point. This is a point on the graph. There's a point at 0, -1. That's my y-intercept. Next, I'm going to find the x-intercepts. To find the x-intercepts are where the graph intersects the x-axis. And along there, our y's are equal to 0. So anytime you're trying to find the x-intercepts of a function, You just substitute in 0 for y. Remember, in this fancy function notation, this f of x, this is the same as if I would replace that with y. Those two things are the same thing. So I'm just going to substitute a 0 in for that y and solve. So I have 0 equals a negative 12x cubed plus 4x squared plus 3x minus 1. And the way I'm going to solve that is I'm going to factor. So first thing I look for when I'm factoring is my greatest common factor. Here I see a leading negative, so I know I need to factor out that leading negative. So I'm going to factor out a leading negative. They don't have anything else in common. So all I'm going to do is factor out that leading negative. So I have 12x cubed minus 4x squared minus 3x plus 1. I can go ahead and divide both sides by a negative here so that I'm not having to worry about that negative along the way. So this side divided by negative 1 is 0, and this side divided by negative 1 makes that 1, and it just leaves me with 12x cubed minus 4x squared minus 3x plus 1. Next, I'm still trying to factor. There are 4 terms here. When there are 4 terms, we attempt to group. So I'm going to look at the first 2, and I'm going to look at the last 2 terms. So I'm just going to group them, and I'm going to find the common factor in those 2. So I'm going to ignore these 2 and just look for a common factor here. There, I see that both of them have a 4, and I see an x squared. So I have a 4x squared from both of those. Then I'm going to divide that out. So 12x divided x cubed divided by 4x squared leaves me with 3x. And 4x squared divided by 4x squared leaves me with 1. Now I'm going to ignore the front part, and I'm just going to look at the back. So that's what grouping, when I group, I'm going to group the first 2, then I group the last 2. And here I'm going to factor out their greatest factor. Well, the only factor they have in common is 1. It has a leading negative, so I'm going to factor out that negative 1. So I factor out a negative 1. It leaves me with 3x minus, that negative changes the sign here because a negative times a negative would make that a positive, 1. I go, hey, look, they match. It's really good when they match. Because when they don't match, then we get really sad. We'll do that in a later video. But right now, they match. Yay! So we can factor out that 3x minus 1 from both of those terms. And it leaves us with 4x squared minus 1. Now, I'm not down to linear terms yet. By the term linear, I mean that the degree on my x's needs to be 1. And this one's not down to that yet. So I'm going to look to factor this further. It's only 2 terms, so I look for a difference of squares. And sure enough, this is a difference of squares. So I'm going to factor that using my difference of squares, 2 parentheses. The signs are different. That's what makes the 0 in the middle. Take the square root of 4x squared and you get 2x. Take the square root of 1 and you get 1. So now I have factored this polynomial down to its linear factors. Notice there are 3 of them. 1, 2, 3. Just like we said there would be. 3 of those linear factors. So now I'm going to solve for each one of those. I set each one because 3 numbers multiplying together equals 0. One of them has to be 0. So that guy set to 0. This guy set to 0, and that one set to 0, and I just solve. So I add 1 to both sides, subtract 1 from both sides, add 1 to both sides, divide by 3, divide by 2, and divide by 2. So there are 3 x-intercepts on this function. The 3 x-intercepts are at the points, because x-intercepts are points on my graph. At 1/3, my y value was 0. Negative 1/2, my y value is 0. And 1/2, my y value is 0. Those are my x-intercepts there. Now, we're going to talk about the multiplicity of each of these. Notice that there's no duplication. There's no double roots. In this case, the multiplicity of each one of those is 1. In other words, the root itself just shows up one time. When the multiplicity is 1, it means it's going to cross at that point. Because this is odd. Because that's an odd multiplicity, it crosses at each point. If they had shown up more than once, if it shows up an even number of times, then it turns at that point. But when it shows up an odd number of times, it crosses at that point. So the multiplicity of each one of these is 1. I'm now going to graph the function. I'm just going to put the points that I know on this graph. So I know that there's a point at 0, -1. I'm going to graph that point, 0, -1. I know that there's a point at 1/3. Counting by these little fractions, I think I'll count by sixths because that's my common denominator. And that way when I graph it, maybe it'll help just a little bit with my graphing. 1/6, 2/6 is the same as 1/3. 3/6 is the same as a half. 4/6 is the same as 2/3. And 5/6 doesn't reduce. 6/6 becomes 1. And I'm going to do the same thing on the other direction. So 1, 2, 3, 4, 5, 6, and that's my -1. And maybe I should even do it on my y-axis so that my scale is the same. So I have 1, 2, 3, 4, 5, 6, and that puts that point at 0, -1. Then this point is at 1/3, 0. Well, 1/3, 0 is 2/6. -1/2, 0. Well, -1/2 is 3/6. So there. And then 1/2, 0 is at 3/6 or here. So once I have my x-intercepts and my y-intercepts on there, I'm now going to look back at my end behavior to help me decide what the graph looks like. I know that it's going to fall on the right. So from this rightmost point, I'm going to make the point fall from that point. I know on the leftmost point, it's going to rise. And then in between, it's got to hit the rest of the points. Plus, the multiplicity tells me at each one of those points it's going to cross, which makes sense because I have to cross here to make it down to this y-intercept. Now, in this class, I don't know exactly where this thing turns. Maybe it comes way down here and then flips back around to hit the y-intercept. Or maybe it hits the y-intercept and then it keeps going and turns. We find those turning points in calculus. We could get more specific in this class by just substituting in some x values. We could put in -1/3 and -1/6 to get a little more exact. But I'm just kind of giving a sketch with those x and y intercepts. So I'm just going to make it cross through here, and at some point it's got to turn back around so that I hit that y-intercept and then I can come back up to this x-intercept. Now, once I get up to this x-intercept, again, because the multiplicity of this is just 1, I know it's not going to turn back around there. It's going to cross through again. So I have it cross through that x-axis. Again, I don't know how high it comes up. Maybe it comes way up here. Maybe it just barely turns around there. But somewhere it has to turn back around to go back through that other x-intercept. So it turns back around so that it hits through that x-intercept. And because the multiplicity of that point, it only shows up one time, and 1's an odd number, I know it's going to cross at that point as well. There, we could be a little more specific if we wanted to by plugging in 1/6, -1/6, -1/3, but there's our polynomial graph. I always like to tell my reader exactly where my points are, so that they're not confused by those points. So I label all my points in here, just so they know these are my x-intercepts, this is my y-intercept, and that again is an x-intercept. I said I was going to have 3, I said it was going to turn twice, and it does look like that original sketch. So there we have fully graphed our polynomial. Math Made Simple at Simpson Math. Thanks for watching.